Welcome back to the Deep Dive. Today we are taking on a module that is absolutely fundamental to modern engineering, Introduction to Stream Computing.
Right.
So if you're a BTech student who's tackling Module 2, this is your shortcut to mastering the high-velocity, memory-constrained world of data that never stops flowing.
And our mission here is to quickly and, thoroughly understand the foundational concepts and maybe more importantly, the really ingenious algorithms, the technical solutions that allow us to process these continuous streams of data efficiently.
That sounds critical.
For sure. If you're aiming for a career in finance, network security, or IoT, these concepts well, they're your daily bread and butter.
Okay, let's unpack this then. We're dealing with the syllabus that's packed with some pretty foundational concepts, but also some tricky names like Flajolet-Martin and DGIM. So before we really jump in, what's the roadmap for this deep dive?
We've structured this to really build clarity. So first, we establish the conceptual foundation. What exactly is stream data, and why does the architecture demand these specialized solutions?
Okay.
We really need to understand the constraints before we can appreciate the algorithms themselves.
The why determines the how. Got it.
Exactly. Then we move into the first wave of solutions, which I'd call efficiency tools. This is for rapid identification and filtering, and we'll focus heavily on sampling and the elegant simplicity of the Bloom filter.
And after that?
Then the main event, algorithmic solutions. We'll spend the necessary time detailing the Flajolet-Martin algorithm for unique counting, the utility of frequency moments, especially M2, the so-called surprise number.
Oh, that sounds interesting.
It is. And finally, the essential DGIM algorithm for efficient window counting.
Fantastic. So let's start with that conceptual foundation. We often use the analogy that traditional data processing is like swimming in a static finite lake. If that's the case, what is streaming data?
Streaming data is a fire hose. It's a river. It's constantly flowing, constantly accelerating, and critically, it is unbounded and infinite.
Unbounded.
Yeah. And the key engineering challenge is that this data has to be processed immediately. We often call this single-pass processing. If you miss a data point or you don't process a transaction within, say, a few milliseconds, you don't get a chance to go back and query it later. It's gone.
So we're dealing with sequences of events, right?
Yeah.
Often arriving as tuples that are tagged with a timestamp. This demand for immediate processing must just drastically change the system architecture.
Oh, absolutely. It completely redefines it.
Compared to traditional relational databases.
It absolutely does. And this is what defines the streaming data model. Unlike traditional systems where, you store all the data and then you query it, stream data needs a specialized streaming data architecture.
And what does that look like?
Well, this architecture has to handle the high-speed data ingestion first. Then the data is pushed through specialized processing element stream processors, and then finally funneled to some limited output or storage sinks.
And the crucial constraint here, and I think this is what drives the need for every algorithm we're about to discuss, is the memory limit.
Precisely. You simply cannot keep the entire history of the stream in memory. It's impossible. If you're processing a billion stock tickers a minute, your memory is finite, which forces you to use approximations, summaries, and these single-pass algorithms.
Right.
That memory constraint is the central narrative of this entire module.
Okay, so here's where the clever engineering begins. Since we can't store everything, we obviously can't analyze everything. So the first compromise is sampling. Why is getting a statistically representative subset the first step toward efficiency?
We rely on sampling techniques for efficient stream processing because they allow us to make really accurate statistical inferences about the entire population of the stream based on just a small, manageable subset.
Like an estimate.
Exactly. For instance, estimating the average load on a server by only looking at 1 in every 100 packets saves immense computational and storage overhead, but it still provides a statistically valid operational estimate.
That makes sense for estimation.
Yep.
But what about a binary decision? Like, is this specific item, say, a known malicious IP address in my massive blacklist set? I can't afford to query a huge disk database for every single packet, but I also can't store the whole blacklist in fast memory.
And that brings us to the Bloom filter.
The Bloom filter.
The Bloom filter is probably one of the most elegant solutions in computer science for filtering streams. The design challenge is exactly that. High-speed membership testing with a minimal memory footprint.
Okay, walk us through how this minimal memory is achieved using, I assume, probability.
It's brilliant, really. Instead of storing the actual set elements, the IPs themselves, we use a simple bit array and multiple independent hash functions.
Multiple hash functions.
Yes. So when you add a banned IP, you hash it, say, $2 times, and you set those dollar resulting positions in the bit array to 1. Now, when a new IP arrives, you hash it the same dollar ways. If all taller of those resulting bits are 1, the filter says the item is probably present.
But because multiple inputs can hash to the same bit positions, there's an inherent risk, right? That's the famous trade-off.
Yes, that's the critical trade-off. High speed and memory efficiency versus accuracy. The filter is probabilistic, which means it can generate false positives.
Okay.
It might tell you an item is in the set when it actually isn't, simply because other items have set all the necessary bits by coincidence.
Okay, so in a network router, using this to filter known bad actors, a false positive means you might incorrectly block a legitimate user for a moment.
Correct. But crucially, and this is the key part, false negatives are impossible. If an item was truly added to the set, its specific bits are definitely set to 1, so the filter will always correctly identify it as present. It will never miss. For applications like network security, where guaranteeing you catch the bad actor is paramount, that tolerable risk of an occasional false positive is a fantastic engineering compromise.
That's a great example of using probability to overcome memory limits. Okay, let's pivot to the trickiest part. Counting. When we can't store all the elements, how do we solve the count-at-distinct problem? How do we find the number of unique users or unique hashtags in a stream with billions of items?
This is a textbook example of a problem that you just cannot solve exactly in bounded memory. So we have to turn to probabilistic approximations, and that's where the Flajolet-Martin Algorithm comes in, or FM.
What's the conceptual breakthrough here? I mean, how do you count something unique without tracking every single unique ID you've ever seen?
It relies on hashing and probability space. So imagine you're flipping a coin many, many times. If you flip it once, the probability of getting tails as 0 is 1/2. If you flip it 10 times and get 10 tails in a row, the probability is 1/2 to the power of 10.
Much, much less likely.
Right. The longer the string of consecutive tails, the fewer chances you had to not get that result.
I think I see where this is going.
FM does something very similar using hash functions. Every unique element in the stream is hashed to a random bit string. We then look for the maximum number of trailing zeros observed across all the unique items we've seen so far. If that maximum trailing zero count is, say, total dollars, the algorithm estimates the total number of unique items is proportional to 2 colors.
So seeing a hash ending in 10 zeros suggests we've sampled a bit space that implies about 1,000 unique elements have contributed to that distribution. It sounds a bit like black magic, but it's mathematically grounded.
It is pure mathematics applied to data streams. And once we can count unique elements, we can move to the next level of analysis, understanding the distribution of those counts using estimating moments.
Okay, explain frequency moments for us. We know M1, the first moment, is pretty simple.
Right. M1 first moment is just the total count of items in the stream. It tells you the volume. But volume alone isn't really enough. We need to know how that traffic is distributed.
And that's where the M2, or second moment, comes in. I've heard engineers sometimes call this the surprise number. Why such a dramatic name?
It's called the surprise number because it reveals data skew. It reveals the unexpected distribution. M2 is the sum of the squares of the frequency of each distinct item.
The sum of the squares.
Yes, and by squaring the frequencies, we disproportionately penalize items that appear frequently.
So if 100 people visit a site once, M2 goes up by 100. But if one person visits 100 times, M2 increases by 100 squared, 10,000. That huge difference tells you exactly where the concentration is.
Precisely. If M2 is high, it means you have heavy hitters items that appear way more often than others, which might signal a hot trend, a major anomaly, or, maybe a bot network sending excessive traffic. It's a vital compressed metric for instantly assessing data skew.
Okay, so we've covered membership testing with the Bloom filter and distinct counting with FM and M2. But those generally cover the entire stream. Our final algorithm, DGIM, shifts the focus to a specific window of time. So how do we count events in a moving window when we still can't store all the data?
This brings us to the DGIM algorithm Datar Gionis Indik Motwani. The problem it solves is efficiently calculating the approximate number of ones, which could represent an event, like a login or a click within a defined sliding window of the stream, like the last 10,000 packets.
Tracking 10,000 items in memory might sound doable, but if the stream velocity is massive, that window is changing every second. We need a way to summarize that window efficiently.
And DGIM's solution is one of the cleverest examples of memory management in stream processing. It divides the stream into buckets. Each bucket stores two things: the count of ones it contains and the timestamp of the last one in that bucket.
And the essential trick involves the sizing of those buckets.
Yes. The crucial constraint is that the bucket sizes must be powers of 2. 1, 2, 4, 8, 16, and so on. And you can only have a maximum of 2 buckets of any single size. So at most, 2 buckets of size 4, for instance.
Why does that power of 2 constraint save so much memory?
Well, this logarithmic structure means you never store too much redundant information. When the window slides and a new bucket of size 1 is added, if you already have 2 buckets of size 1, they are immediately merged into a single bucket of size 2.
Ah, and that can cascade.
It does. If you now have 3 buckets of size 2, 2 of them merge into a size 4 bucket, and so on. This merging cascade ensures that we only need to store a logarithmic number of buckets relative to the window size by doing a fast, memory-efficient approximation of the event count.
So it sacrifices perfect exactness for speed and critically guaranteed memory limits.
Precisely. To answer a query about the window count, you just sum the ones from all the full buckets, and then you only need to approximate the count in that final partial bucket. It's an incredibly elegant solution for real-time monitoring.
Okay, let's connect these theoretical tools back to the real engineering world. Where are these algorithms and concepts actually performing work right now?
Well, if we look at finance, stream processing is just non-negotiable. High-frequency trading firms use moment estimation M2 to calculate volatility and detect massive unexpected shifts in volume instantly.
In microseconds.
They need these approximations in microseconds to execute trades. It's that critical.
And what about for security and network management?
In network monitoring, this is where all 3 algorithms often work together. You'll have Bloom filters sitting at the edge routers to instantly drop packets from known malicious IPs. Then you'll have DGIM tracking the rate of connection requests to identify a spiking DDoS attack against a server cluster. These tools provide that necessary instant visibility to respond to threats.
And finally, what about large-scale platforms like X or YouTube dealing with truly global data flows?
When you're analyzing social media streams or sensor data in IoT, you rely on Flajolet-Martin to understand popularity. If you want to know how many unique people viewed a video or how many unique devices are sending telemetry data, the sheer scale makes exact counting impossible.
So approximation via FM is really the only way to get real-time analytics.
It's the only route.
Okay, moving into the exam zone, let's nail down the non-negotiable points the listener needs to master for the KTU assessment.
Right. The ability to compare and contrast the different algorithms is absolutely crucial.
So let's start with the basics. What are the key definitions they need to know?
You need a clear, concise definition of a data stream unbounded, high-velocity single pass. And you have to understand the purpose of sampling, obtaining statistical representation under bounded memory.
Okay, and the Bloom filter.
For the Bloom filter, you have to understand the mechanism of using multiple hash functions on a bit array. But the key testable insight is that trade-off. False positives are possible, but false negatives are impossible. You must be able to articulate why that makes it so ideal for blacklisting.
And what about the difference between the 2 main counting algorithms?
This is a major point. Flajolet-Martin is for estimating the number of distinct elements in the entire stream, and it relies on the trailing zeros of the hashed values. DGIM is for calculating the approximate count of ones within a specific, much smaller sliding window, relying entirely on that power of 2 bucket structure.
2 very different use cases. And the second moment.
You need to know the utility of the M2 moment, the surprise number. Its purpose isn't just counting, it's about detecting heavy hitters and measuring data skew. That's fundamental for anomaly detection.
So we've established the memory constraint, explored 3 ingenious algorithms that get around that limit, and seen their real-world applications.
To summarize the 5 core insights of stream computing, I'd say.
Go for it.
1. Processing unbounded, high-velocity data requires real-time, single-pass approximate solutions, because exact storage is impossible.
Okay.
2. The Bloom filter offers high-speed membership testing, guaranteeing 0 false negatives while tolerating a measurable false positive risk. 3. The count distinct problem is solved approximately by Flajolet-Martin using probability inferred from trailing zeros in hashed values.
Makes sense.
4. Frequency moments, especially M2, are critical for estimating data spread and detecting those high-frequency elements, the heavy hitters. And finally, 5. The DGIM algorithm efficiently approximates event counts in a sliding window by maintaining a logarithmic memory structure using power of 2 size buckets.
Now that you understand the fundamental engineering challenge posed by continuous data flow, consider the architecture of a global sensor network. If you had to select only one of these three algorithms, Bloom, FM, or DGIM, to guarantee the network remains stable and responsive under unexpected extreme load, which one would you choose and why? That's something worth exploring as you continue your studies.